Hi, welcome back to differential geometry. So today, the topic of our discussion will be on vector fields. So you've probably heard of vector fields before because they're applications in physics. That is, force fields such as magnetic fields or gravitational fields is where these generally show up. So these fields, they show both the magnitude or the strength and the direction of any force of a force at any point. So this picture, for example, is it's a vector field in R2. We'll be working in R3, but the idea is the same. So at any point, we have at any point we can draw an arrow, and that arrow has both a direction and a length. And that tells you the strength of it as well as the direction of the force as well as the direction of it. And we can tell in this particular example, the point 0, 0, it is actually not drawn as an arrow, it's drawn as a point, and that just means that at this point, it's actually the zero vector. So there's no force acting on it, according to this past physics interpretation. So next I'm going to define this a little more rigorously. Okay. So, definition. A vector field is, or on R3, since that's where we're working, it's a function that assigns to each point P of R3 a tangent vector v of P and to R3 at P. So intuitively, what this is saying is that a vector field is just assigning a single tangent vector to every point of R3. Okay. So we can also define addition and scalar multiplication of vector fields fairly naturally. So we're going to begin first with addition. So we can define v plus w of P, and we're just showing this at a single point, this works at all points P, is equal to v of P plus w of P. And the idea is that this construction, it allows you to construct this, it allows you to determine what this value is at this point, but since we can do it at every point, that allows us to find the whole structure. This is called this allows us to define v plus w. So that's the idea behind this. And this is what the author refers to as the pointwise principle. And so, in other words, we can add v and w by adding their values at each point, rather than, well, we can just, yeah. And we can extend that to the functions themselves. Okay, so for a quick picture in R2 rather than R3, since R2 is easier to draw, we can just draw two tangent vectors at a point, v sub p and w sub p. We can add them as we normally would by drawing the parallelogram and just connecting it. So this is your new vector v sub p plus w sub p. And the only difference in R3 is that you would draw the parallelepiped instead. Okay, so we're going to use the pointwise principle again to define scalar multiplication on the tangent spaces of R3. So here the scalar will be a function, or in particular it's a real valued function on R3. And V is a vector field, and we're going to let f be a real valued function, and this is our scalar, and V a vector field on R3. Okay, then fv of p is equal to f of p, v of p, for all p in R3. Okay, so at each p in R3, we can think of v of p as being scaled by a factor of f of p, and that's just a real number. So as an example of this, we can just write this up. We're going to say that f of p is equal to x, y, z. V of p is equal to the tangent vector 1, 2, 1 sub p. And we're going to say p is equal to 2, 3, 4. Okay. Then f times v of p is equal to f of p v of p by definition. Which is equal to, just substituting in f of p, 2 times 3 times 4, v of p, which is, well, we'll leave that out for now, just write it in the next step. Okay, this is 24 v of p, and this is what I was saying before, that it's just scaling the vector v of p by 24 in this case, but just f of p, which is just a real number. Okay, and writing this out more explicitly, 24 times 1, 2, 1, which is v of p, and that is equal to, just by the definition of multiplication here, it's 24, 48, 24, evaluate at p, or the tangent vector at p. Okay, so that is our example here. So this is all really nice because it's, well, using these definitions for vector addition and scalar multiplication, we can show that vector fields are a vector space, which just gives this all a really nice structure. I'm not going to prove that now, and that's where I'm going to end the video. So thank you for listening again.